Okay, so we've got a roller coaster that's going through a couple,
Just one dip and then coming back to, yeah, one dip and going up to another high point. And then
and the next high point's not as high,
it's not as high, and then it comes down, goes to a flat.
kind of like that.
Mhm.
So we've got a roller coaster starting up here, and it said this was a height of 34 meters.
35.
So we've got a 35 meter initial drop.
So you didn't decide to go play Mario Kart?
Did it say how high up this next hill was?
26 meters, actually, yeah.
So that's,
And the flat is 14 meters. From the bottom of the trough.
oh, I see. So it doesn't come all the way back down. This is 14 meters. Cool. All right. So this have multiple parts.
Yeah, it does, actually.
So assuming no friction, calculate the speed at point 2. So we're releasing our roller coaster from rest at point 1. And so you already mentioned this. All of its energy here is going to be what type of energy?
Potential.
So we've got potential energy, which the equation for that is
1/2
MG1.
mgy. Yeah. You were just going to give us the next equation.
Yeah.
That we need.
Is 1/2 mv squared.
Good. So down here, all of our energy is going to be kinetic, and it's going to be equal to 1/2 mv squared. So what type of energy are we going to have here?
Potential again.
We're actually going to have a
both 'cause
mixture.
Yeah, because it didn't come up as high.
Exactly. So we'll have a mixture, and what kind will we have? Does it ask about this point ever?
No, wait a minute. Yep.
So what kind of energy will we have here?
A mixture.
A mixture again.
But a less of a mixture.
Yeah. So here we're going to have what's going to be more, potential energy or kinetic energy?
Potential.
Yeah, probably because we came up pretty close to, well, 26 of the 35
About
meters.
3/4 of the way up again.
Here, relative to this point, we're going to have more of our energy as kinetic energy than we did here. So those are kind of just some like quick observations, and now mathematically we can go through and start figuring out what those mixtures are. So potential energy we can calculate. Does it give us the mass of the roller coaster? No. So we can almost calculate it, but we're going to have a little bit of symbolism in it. So we don't know the mass. We do know that gravity, though, is 9.81 meters per second. And we do know that the y, or the height, is 35 meters.
And that's gonna cancel out anyway, though?
Mm-hmm. So we can do 9.81 times 35. So our potential energy, and actually our total energy, because this is all the energy that we get. Whatever energy we have right here, we're stuck with, because we're not going to lose any and we're not going to gain any, because this is a friction-free roller coaster. We don't have any like other forces. It's not like we're going to get hooked up to a chain right here that's going to pull us up and give us more energy. So this is like our total energy. And it's 343.35 M. So down here, we know that we are going to have that same amount of energy, but now it's going to be in a new form. So instead of being potential energy, it's now kinetic energy, but it's still the same number. And we don't know what that number is fully because we've got this variable in there. But that's okay, because if we say that the potential energy here is going to equal the kinetic energy here, we can set this equation equal to this equation, and we can say mgy equals 1/2 mv squared. We see that there's cancellation of the m's. We already know that g times y, because we did it up there, is 343.35 Now on this side, all we have is just that one variable, and it's the variable that we're looking for. So now we can solve algebraically.
So we divide that by 1.
Yep, divide by 1/2, multiply by 2, same thing, and then take the square root, and we get 26.2 meters per second equals V. So that's part one, because it was asking for what's the speed at the slow point.
26.2 meters per second. Not squared. That's the speed.
Correct.
Okay, then at point 3. So point 3 is right there at 26 meters. Where it's mixed, but mostly potential.
Yeah, so now we know we still have the same total amount of energy, so that 343.35 M number. And now we know that we've got a mixture. Part of that is going to be potential energy, and part of that is going to be kinetic energy. So we already know that we're going to have, so let's come up with like a little symbolic equation here. Total energy is going to be equal to potential energy plus kinetic energy.
So that 343.
Yeah, so our total
Equals-
energy, we can express it, like you said, 343.35 M.
Then we'll have to do 26 times 9.81 for the potential.
Good, so MGY is going to be M, G, Y,
26 high this time.
and then 1/2 M V squared. So we get cancellation of the M again, since it's in every term, that just goes away. We can multiply that to get some number. So, I'm gonna continue it down here since I'm out of room. So 343.35 equals 1.81 times 26 to 55.06 plus 1/2 V squared. So again, because of cancellation, we end up with an equation that only has one variable, so we can solve.
13.1.
So I got 13.29 meters per second equals V. And that makes sense because we wouldn't expect it to be any bigger than what it was here. We know it's for sure going to be slower. So here we were at 26 meters per second. Now we're at like a little bit more than half of that. So logically that checks out. And we have the math to back it up.
So for some reason, well, I guess no, velocity, yeah. I would want to put that, 26.2 meters per second in with a V squared up there for that equation. And that would totally screw everything up.
Yeah, because this kinetic energy here is not the same as this kinetic energy here. So we can't use the same velocity because we know that down here the velocity was 26.2, but as soon as it starts going up this slope, it's going to start slowing down and it's going to convert energy from kinetic energy into potential energy. And then that conversion is going to tap out right here. And then we're going to have some mixture of potential energy and kinetic energy, and then we're going to start transferring back
Gotcha.
into kinetic energy.
So it's a whole new equation. We take the total energy that we found on the last equation, and then we add it to the new potential and the new kinetic for the next point.
Good. So yeah, the one thing that remains constant all throughout is this equals our total energy. So we're going to keep referring back to that number.
And just plug in your new potential and kinetic
Mhm.
energies.
So with point 4, which is the next one,
Yep.
It's just pretty much the same thing as what we did for point 3, just, but it's totally new kinetic energy.
Yeah, so we can't carry over any
It's the
emerging
same
numbers, so,
process.
but we can use this exact same equation.
Okay.
Total energy equals some combination of potential energy and kinetic energy. So again, we would say TE equals PE plus KE. Plugging in our numbers, we would get 343.35 M equals M G Y plus 1/2 MB squared. M's go away.
16, 14.
And I got 20.3 meters per second equals V. So order of operations, multiply those two things together, subtract it over to this side, divide by 1/2, and then square root both sides. That's how we get to 20.3 equals
So that's
V.
faster right there
Yeah,
than it was.
faster
Because
than
it
this
just went
point,
down.
but slower than this point, right? And that makes sense because it's, as we go low, we go fast because we're converting from potential energy into kinetic energy. So here was our absolute fastest point, and then this was our next fastest point, this was our next fastest point, this was our slowest point.
26.2, 13.29, then back to 20.
Yep.
20.3.
So we went from 0 to 26-ish, to 13, to 20. So that's a good review of energy and how it
Yeah, it is.
converts between the two forms. And so if we had a friction, then that'd be a whole nother factor that we have to take into account. But luckily this was a friction-free question, which isn't realistic, but it is nice mathematically.